n equals 2 matter. So you should think of all these this temperature being T greater than the Hawking-Page temperature. This is all temperatures for which the n equals 4 theory is already in its deconfined phase. So the gluons are, Zn symmetry is broken in this case. There's no Zn. So there is a critical temperature at which, in this case, the mesons, above which the mesons get, mesons melt, and the quarks are liberated, and then you can study the same thing at finite temperature, and you get a picture like this. And what happens here, to my understanding, at low temperatures is quite intricate, and it's not even clear whether at low temperatures the probe approximation can even be trusted. So apart from this particular region, I think it's true that this diagram, this phase diagram, can be interpreted as bound state of mesons, or bound mesons and melted mesons. And this is a first order transition. Okay. You can in fact do a little bit more. You can. This is something that we did with a lattice gauge theorist, because this person was asking us, my colleague in Swansea was asking, what happened. Probably we have already had lectures on lattice simulations at imaginary chemical potential, because on the lattice there is a sign problem.
So the TC is less than the Hawking-Page temperature.
This is everything here is greater than the Hawking-Page temperature.
I mean, here's temperature, right? So where is the Hawking-Page temperature?
Where is the
Hawking-Page temperature.
Yes. So Hawking-Page temperature. Okay. So all of this analysis is usually done in the limit where this black hole is represented by a planar black hole. So it's arbitrarily large. I don't know if the same analysis has been done in the case where of a spherical black hole. Do you know if it has been done? So I don't know if this analysis, if I was doing this honestly in the AdS Schwarzschild with a spherical horizon, then the Hawking-Page temperature would appear somewhere here. But normally it's all done in the flat, the case of the planar black hole. So the question is, what happens in the system if you have imaginary chemical potential? And it's possible to turn on an imaginary chemical potential. It's just that you don't want to do it usually in AdS CFT because there's no sign problem. However, when you have imaginary chemical potential, there are general arguments by which you can show that the theory should have kind of an interesting behavior which actually is reproduced by these probe brains. And so if you plot T versus imaginary chemical potential, which means actually that mu square is less than 0, here mu square is greater than 0. You can do an analysis which is similar, but there are some subtleties which make it different, and you find that actually in this case the system has these kinds of phase transitions where you have a bound meson phase here and meson melted, and then you have new first order transition lines, and these transition lines are called the Roberts-Weiss transitions. So probably you can go back and look up what Roberts-Weiss transitions are, which are well known on the lattice. And it turns out that the AdS CFT setup actually reproduces these Roberts-Weiss transitions. All the lines in these diagrams are first order lines. So this point here where a first order transition line meets these first order transition lines is like a triple point. Okay, so the point, all I want to make is that there are lots of, can we have the, projector? So there are many features of gauge theory, both with and without fundamental matter, that we can sort of understand at the simplest level in the holographic setups, where everything is in control. The next natural question is, there's a lot of work that has been done in the context of these flavors in the quenched approximation. The interesting question is whether one can actually go beyond the quenched approximation and include quark flavors when the number of flavors is comparable to NC, comparable to the number of colors. Because that's the most interesting situation. So this is actually a talk that I gave somewhere else, so apologies, but you will see that there's lots of things that I said that already appear here. Right, so the motivation for what I'm going to tell you in the next half an hour is pretty much this idea. Actually, you know, this graph, which we now have seen several times in various guises. I mean, this graph was something that my lattice colleagues in Swansea used to flash a lot. And then one day I talked to each one of them and then found out that, well, there was this question mark. And now I think that this question mark region should be expanded to cover this whole diagram. Okay, I think that is the current situation. Given that that's the current situation, I think that it calls for some systematic approaches, at least coming from the holographic side or the AdS-CFT side. No, I'm not saying that the AdS-CFT or holography is going to answer these questions, but at least we can try and learn something about physics. So the key problem seems to be what happens at high densities as opposed to high temperatures. So high temperature region, of course, is accessible to the lattice, and finite chemical potential or finite baryon number chemical potential is pretty much inaccessible to the lattice because of the sign problem in the lattice. So and then there are all these effective models that we have heard about this morning, which give us some information, perhaps exceedingly rich information about what happens there. But then, is it working? It seems to be working a little bit. Okay, so there are some features that we might want to understand about regions where the chemical potential or the density the quark density is large. We know what to do in this region where the chemical potential is asymptotically large, and if we are in QCD, we know how to use asymptotic freedom and understand that regime. So what I wanted to actually give you some idea of is what we can do with the AdS-CFT correspondence, if you wish, the top-down approach. Actually, I can't remember which is which, top-down or bottom-up. So what the AdS-CFT correspondence can actually tell us about large NF limits, when you have the number of flavors or number of quarks being comparable to the number of colors. Now, this is actually conceptually, this is a very difficult problem. Even in AdS-CFT, by the way. And the point is, this particular limit where n is large and nf is large is the so-called Veneziano limit, where you take n to infinity, nf to infinity, keeping n over nf fixed. Okay, there are conceptual problems with actually trying to argue that such a limit might be accessible in a classical AdS-CFT picture. There are conceptual arguments, and I might just mention a couple of them. There are reasons to believe, following from some recent work, that probe approximations, like the ones that we have discussed, and there were signs of this before, is that probe approximations may not be consistent when you talk about the system at arbitrarily low temperatures. There are reasons to believe this, and so that means that whatever we do is quite important from the perspective of AdS-CFT. I don't know whether we will ever be able to answer this problem, but from the perspective of AdS-CFT, it's kind of important to understand how we might be able to describe a high density state of quark matter in some limit that looks like a Veneziano limit. So the Veneziano limit, if you recall what it is in the language of large N theories, we know that the 't Hooft expansion just corresponds to a genus expansion. I don't know if this is kind of visible, but this is the genus expansion that I kind of described yesterday. when you introduce flavors into the theory, quark flavors, into each of these Riemann surfaces of a fixed genus, you start introducing holes or windows. And then any quantity that you compute, the free energy, for example, it not only now depends upon n as n to the 2 minus 2g, but it also depends upon this ratio nf over n raised to certain power, where w here is the number of windows in a graph. And you can argue, I mean, there are string theory arguments which tell you that this nf over n is actually equivalent to something that we call the effective open string coupling on the probe or flavor brains. So if nf over n is of order 1, then the effective open string coupling on these probe brains is of order 1, and then you don't have a way to use weakly coupled string theory or even classical supergravity to understand what's going on. So it's actually, there is a conceptual problem in asking whether we can use AdS CFT to describe a Veneziano limit for a gauge theory. But what I'm going to do is adopt a constructive approach, and we've already seen how weakly coupled gauge theory. So this is good. I wasn't pressing it hard. So we've already seen that. Okay. Already seen that weakly coupled gauge theories are kind of an interesting way to see non-trivial thermodynamics, and they reproduce non-trivial thermodynamics at strong coupling. So what we can ask is, we can begin by asking, what if we modify the analysis that we just went through of n equals 4 super Yang-Mills at large n on S3 cross S1, and we modify the analysis by studying not just n equals 4 but some theory, right, which has similar matter content as n equals 4, or maybe it's just pure Yang-Mills, right, doesn't have to be n equals 4, but you add to it a large number of quarks in the fundamental representation. Okay, so take your favorite example of a gauge theory with your favorite matter content, including matter fields in the fundamental representation. Just make sure you scale the number of matter fields in the fundamental representation in the same way as the number of colors. So you take NF and NC both to infinity. Put the theory on finite volume, exactly as we did before, S3 cross S1, right? Ask what is the phase diagram of that system. Okay? So we do the same exercise that we did for n equals 4. So we have this theory on S3 cross S1. We introduce the Polyakov loop, which is the lightest mode on S3 cross S1, integrate everything out, and do everything in the presence of a non-zero chemical potential for baryon number.
This is the weak coupling limit?
Yeah, this is the weak coupling limit, okay? Because it's the limit that we can do. So you do the weak coupling limit, and you do this with chemical potential. Okay, so what you will find is that the action, in addition, these dot dot dots ignore are the terms that you would get if you were studying n equals 4 theory. So I haven't written them down. N equals 4 or pure Yang. In this case, when you have fundamental matter fields, you get new contributions. Okay, these new contributions, they are exactly like the contributions that you would get from the free energy for an ideal gas of fermions, except that the presence of the Polyakov loop matrix actually weights these Boltzmann factors in a particular way. For the quarks, it comes with a U. For the anti-quarks, or it comes with a U dagger. And similarly for quarks, which carry quark number +1, you get this sign for the chemical potential. And for quarks, for anti-quarks, you get a plus mu. Okay? And clearly, this action shows us the origin of the sign problem. The point is that this action is not Hermitian. And it's not Hermitian simply because there is a non-zero chemical potential. So if it was Hermitian, dagger of this should give you this, but it doesn't, right? So that's the origin of the sign problem. The sign problem occurs because you have a breaking of charge conjugation symmetry by introducing the chemical potential. So you have a matrix integral with an exponential in an action which is actually not Hermitian. It's complex, right? Can we solve this system? The answer is actually yes. You can study this system in the large NC, large NF limit, in the Veneziano limit. In that limit, you're going to look for a saddle point configuration. So you think of this as a generalized contour integral, and what you're looking for is a saddle point in this configuration space. So when nf and n go to infinity, there is a complex saddle point that dominates. In fact, there is a configuration of these eigenvalues which I introduced earlier, these alpha i's, which because now you're looking for saddle points in this complexified configuration space, these eigenvalues no longer need to lie on a circle. They just need to lie on some curve in the complex plane. So it turns out that these kinds of matrix models, large-end matrix models, they have a very interesting phase diagram. And I will talk about the phase diagram at fixed low temperatures because that's what's interesting. And what happens as you crank up the chemical potential. So for low baryon number chemical potential, you find that the eigenvalues, these alpha i's, are lying around a closed contour in the complex plane. When you increase the chemical potential, that turns out to be a critical value of the chemical potential at which this distribution picks up a gap. And you can see all of this analytically. Okay, it's just complex analysis. So you find that there is a gap opened up, and in fact you can check that in this phase the Polyakov loop vanishes. You can compute the Polyakov loop in this phase, and you can see that it vanishes. In fact, it's interesting. Trace of u, the expectation value of trace of u vanishes, but expectation value of trace of u dagger does not vanish. And that kind of shows the breaking of charge conjugation symmetry. Here in this phase, both trace u and trace u dagger are non-zero. So we interpret this as a deconfinement transition, and you can also show that this transition is a third order deconfinement transition. And so there's a story, which the summary of which is that you get this rich phase diagram. So I'm talking about yes.
In a previous case,
yes,
you identified the working page phase transition to the deconfinement phase transition, but now it's different.
Right. So the point is, in the previous case, the deconfinement transition was Hawking page, and that was given that you could see in the bulk. In AdS5, you could see that in anti-date, right? You see that, and you have an analog. You have an explanation of that from weakly coupled gauge theory by looking at the eigenvalue distribution for these Polyakov loops, right? And so you have a weak coupling explanation or a picture of that. Here, we don't have a strong coupling picture of what's happening. We are trying to construct, we are trying to see what might happen at strong coupling and then shoot for something like that at strong coupling. So what we are doing is first looking at the weakly coupled picture and see what happens in general. And this does not rely on supersymmetry, it does not rely on any details of the theory. It just depends on there being a gauge theory and matter fields in the fundamental representation. Okay? So as long as you have those conditions satisfied, everything that I'm telling you is generically true. For the theory at finite volume, at weak coupling and large N. Okay, so what happens then in this case is with NF and N both comparable and large, you find that there is a deconfinement transition of the type I mentioned before, but this deconfinement transition is now smoothed to a third order deconfinement transition. It's not first order. It's first order if you have just pure glue or pure Yang-Mills or pure n equals 4, but once you have matter fields and you're in the Veneziano limit, as you might expect when you have quarks in the fundamental representation, you don't expect deconfinement to be a sharp transition anymore. Okay, so this is the analog of what we might expect. It's only because we are at large N that there is a non-analyticity. If you were not at large N, it would be just a smooth crossover. Okay? So there is a transition in this case between a confined phase and a deconfined phase. And then, curiously, as you crank up the chemical potential further and further, you enter into Higgs phase. If you're in a supersymmetric theory, this Higgs phase, or if you're in a theory with at least 8 supersymmetries, which means n equals 2 or n equals 4, you will find that this Higgs phase corresponds to a runaway. Okay, it will be if you have n equals 2 supersymmetry, you'll find that this Higgs phase is actually a runaway unstable direction for the same reasons that I mentioned before. There was a moduli space to begin with, then you introduced a chemical potential that destabilizes the moduli space. But if you don't have that much supersymmetry, then generically this will be a Higgs phase, with a stable condensate. Okay, so the picture is now beginning to look a little bit like what you might want for a theory like QCD. You have a phase that you can call confined, and then a crossover to a deconfined phase, and as you increase chemical potential, you have two phase transitions, or you have at least one phase transition, and you eventually enter into a Higgs phase. The Higgs phase is the analog of the color superconducting phase. Color superconducting is nothing but a Higgs mechanism. Okay, so if you think of color superconducting as just a Higgs mechanism, this is a reasonable toy model to shoot for. So the real question that we have is, can we construct, or can we begin to look at a holographic model that reproduces this kind of a phase diagram? Okay. The answer is, I don't know. We haven't found. Okay. But there is an interesting thing to ask. If there is this Higgs phase, then let's look at the arbitrarily low temperature regime, because that's somehow the most interesting regime when it comes to dense quark matter. You're interested in a regime where the theory is at large baryon chemical potential and low temperatures, and you just want to understand what the phase of dense quark or dense baryonic matter looks like. Now this plot tells us that if we go down to the zero temperature phase, there is a phase here with non-zero baryon number density and a non-zero condensate, okay, at zero temperature. And in this phase, along this axis, the theory is deconfined. And it's deconfined only because you have a huge density. You have a huge quark density or baryon density. So this is deconfinement driven by density as opposed to temperature. Now, if you're an AdS CFT person and you say that you have a state, you're trying to look for a state that is a deconfined state, that means in AdS CFT looking for a solution that has a horizon. This is typically the guideline, that your deconfinement means that there's a horizon. So you want to find some solution that describes a state of dense quark matter that looks like it has a horizon. And so if it has a horizon, that basically tells you that there will be no explicit baryons in the system. The baryons will be deconfined into quarks. So that's basically what our starting point was, to look for states like this in AdS CFT or in type 2b supergravity. This is just you can just skip through this. I just wanted to mention here that there's a very interesting reason why there is this deconfinement transition. It's actually a large N effect, and it can be understood by the fact that when NF and N are both large and taken to infinity, you can understand this phase transition at zero temperature, the zero temperature third order deconfinement phase transition. It can be understood in a very simple way by realizing that if you look at the spectrum of states of this theory, the gauge invariant states, the theory will contain baryon-like objects because it has quarks. So there are gauge invariant baryon-like objects in this theory. If you look at the degeneracy of these baryon-like operators, you'll find that the degeneracy actually grows exponentially with n. So as n goes to infinity, each baryon state that you have in your theory has a degeneracy that itself grows exponentially with n. Okay? That degeneracy is ultimately what's responsible for this deconfinement transition. And it's a very simple argument which I can explain later.
Actually, Fred, right, so another way to view this D3, D7 system is if we begin with from D7 brain warm volume perspective, D3 is basically an incidental.
Yes.
No chemical potential.
I was going to actually mention what you were talking about because you did this work with Hashimoto. So I was going to mention that, I was going to mention that in the end.
Okay.
Because that actually provides us with an inspiration to look for something.
Yes, that's
Okay?
right.
So I'm going to cut this story short very quick because I have 5 minutes left. So the way I'm going to describe this is, so what we're going to look for is not this entire phase diagram. What I'm going to begin by looking for is asking a limited question. I want to look for a gravity background which I can identify with a large density of quarks, where the number of quarks is a number that scales with n squared. Okay, the number density of quarks is such that it's comparable to n squared, so that it's comparable to the action, the basic action of the glue sector. Okay, so the way to understand or the way to realize that is So this question here, what we want to understand is a holographic state that describes quark matter at high densities. And so we want to take a large number density of quark flavors in AdS CFT and begin by asking what is the gravity dual of a state with an order n squared density of quarks inside n equals 4 super Yang-Mills. So I have this n equals 4 theory, which is described by AdS 5 plus S5. I want to start introducing quarks into that theory. And I want to begin by asking a simplified question. Let's just take heavy quarks. Let's not think of light quarks, let's just think of heavy quarks. And let's introduce a lot of them and construct a state which looks like it has a density of order n squared. Heavy quarks. Now a heavy quark in n equals 4 theory, a state with a single massive fundamental representation, a quark in string theory language or D-brain language just corresponds to a fundamental string. Okay, that's generally the picture. That was also the picture that I sketched in the D3, D7 system. So whenever you want to think about quark states, they just correspond to strings. Okay, so okay, so the question that I want to ask is, what happens if I take a single heavy quark in n equals 4 theory and then smear it, consider a smeared distribution of such heavy quarks in n equals 4 theory, such that the density of heavy quarks is order n squared. The corresponding statement in AdS CFT is that you take a bunch of strings, infinite strings inside AdS 5 cross S5, and you take a large number of these strings and you just smear the string distribution along the gauge theory directions. So pictorially what this means is here is the boundary of AdS 5 plus S5, or boundary of AdS 5, and this is what we call the ultraviolet usually, and this is the infrared. So what we want to do is if you want to introduce a single heavy quark here in the boundary theory, you introduce a single fundamental string. You want to introduce a large number of these guys, you just introduce a large number of fundamental strings. Okay? And in fact, you get a distribution. You're looking for a smooth distribution of these fundamental strings. But what you're asking is something more non-trivial. You just don't want to just introduce these strings. You want to ask how these backreact on the geometry. What happens when this backreacts on the geometry? That is what allows you to go beyond the quenched approximation. Okay? So this backreacted geometry is something that we can actually find analytically. Yes, in some cases. And I will just cut to the chase because there's a lot of technical stuff here which is not worth explaining at this point. Is that you can do this problem in type 2b supergravity starting with a geometry that in the ultraviolet looks like AdS 5 cross S5. So the full geometry corresponds to something that exhibits a renormalization group flow from AdS 5 cross S5 in the UV, which is n equals 4 supersymmetric Yang-Mills. But in the infrared, this geometry actually exhibits a new scaling regime. It flows to a scaling regime which is non-relativistic and is described by the so-called Lifshitz scaling symmetry. This is a scaling symmetry which is in which the spatial and temporal directions, they scale differently, but they leave the theory invariant under this transformation. So of course the finite density breaks Lorentz invariance, so you should expect that the theory is not Lorentz invariant. But what is interesting is that AdS CFT predicts that a finite density of quarks, of heavy quarks, will lead to a flow to a new fixed point or to a new scaling solution which has this Lifshitz scaling symmetry. Okay, so those are some plots. It turns out that this